Welcome back to the deep dive.
Yeah.
It is unbelievably the year 2026.
Which is just wild to think about.
It really is. And, if you look around at the digital landscape right now, it is absolutely saturated with generative AI.
Oh, completely. It's everywhere.
I mean, it's writing our emails, it's generating our code, it's creating art. It's virtually the operating system of reality at this point.
Yeah, it feels ubiquitous, almost like it's always been here.
Right. But the truth is, and this is why we're doing this today, this entire revolution can be traced back to a single moment.
A Big Bang event, if you will.
Exactly,
Yeah.
a Big Bang.
And it's not often in the history of technology that you can pinpoint the exact moment everything changed. Usually it's a slow drift. But in this case, we actually can.
We really can. So today, for you listening, we are hopping in a time machine. We are going back less than a decade, which I know feels like a century in tech years, but we are going back to 2017.
Such a massive year.
Huge. We are diving deep into one of the most influential papers, arguably, of the last 20 years. It's titled, Attention is All You Need.
Yes. Published by Ashish Vaswani and his colleagues at Google Brain and Google Research.
Right. And we pulled this from a feed dedicated to state-of-the-art papers. But honestly, state-of-the-art doesn't even feel like a strong enough term for this one.
No, it's foundational. It is the paper, the one that started it all. If you're listening to this and you use ChatGPT or Claude or Gemini or whatever the flavor of the month is in 2026.
Which changes every week.
Exactly. But you are using the technology described in this specific PDF.
So our mission today is to unpack the architecture they introduced, the transformer. We really need to figure out why it rendered the old way of doing things completely obsolete.
And how it paved the way for the AI world we live in right now.
Right. So to understand that, we have to look at the before times. We have to understand the bottleneck that existed before 2017.
Because before this paper dropped, language models were, they were struggling.
They were a bit dim.
Yeah, they were slow, they were sequential, and quite frankly, they were forgetful.
And forgetful is not a great quality in an intelligence.
Not at all. And the authors of this paper propose a really radical idea. They said, effectively, throw out everything you know.
Just scrap it.
Right. They said you don't need recurrence, which was the absolute gold standard at the time. They said you only need attention.
Attention is all you need. It's a very bold title, very confident.
And it is.
But let's unpack the problem first. Paint the picture of that pre-2017 landscape for me. What were the dominant species of AI models roaming the Earth back then?
Okay, so if you were doing sequence modeling, things like language translation, say English to French or text generation, the kings of the hill were recurrent neural networks, RNNs.
Okay, RNN.
Specifically, complex versions of them called LSTMs, which stands for long short-term memory networks, and also gated recurrent networks.
But how did these old kings rule? Like, what was their core mechanic?
They worked sequentially. That is the absolutely key word here, sequential. Imagine you're reading a sentence. These models would process the first symbol or word, generate a hidden state.
Which is basically a memory of that word.
Exactly, a memory representation, and then they pass that memory to the next step.
Okay, so step by step, like reading a book through a straw, just one word at a time.
Precisely. To understand step T, the word you are currently looking at, you absolutely needed the hidden state from step T-1.
Oh, I see.
The computation was factored directly along the symbol positions. You just couldn't skip ahead.
Right, and knowing what we know about computers and efficiency, that sounds like a massive traffic jam.
It was a huge bottleneck. Because step 5 depends entirely on step 4, you cannot parallelize the work.
You can't have 5 different processors working on 5 different words at the same time.
Nope. Because the 5th processor is sitting there twiddling its thumbs, waiting for the 4th processor to finish its job.
Which is just a tragic waste of GPU power. I mean, we have these massive supercomputers capable of doing thousands of things at once, and we're forcing them to stand in a single file line.
Exactly. It severely limits your training speed, and it limits your batch, like how much data you can feed it at once.
Right.
But there's another problem, perhaps even more annoying than the speed issue. It was the long-range dependency problem.
The forgetful part you mentioned earlier.
Yes. So imagine a really long sentence, or even a whole paragraph. Maybe the subject is at the very beginning. Let's say the asthmatic astronaut.
Okay, the asthmatic astronaut.
Right, and then you have 50 words of heavy description about the spaceship and the stars, and finally you get to the verb coughed.
The asthmatic astronaut. Coughed. Got it.
In a sequential model, that crucial information about the astronaut has to survive through every single step in between to reach the verb coughed.
It has to be passed from word 1 to word 2 to word 3, all the way to word 50.
It's exactly like a game of telephone.
Oh, wow. Yeah.
By the time the model gets to the end of the sentence, the signal from the beginning has often just faded away or gotten distorted. The model sees the word coughed, but it has completely forgotten who coughed.
So the context is just lost.
Totally lost. In older models like convs2s or ByteNet, they tried to use convolutions to help with this. But even then, the number of operations required to relate two word positions grew with the distance between them.
So the further apart they were, the harder the math it got.
Exactly. In some cases, it grew linearly, in others logarithmically. But the point is, the further apart two words were, the harder it was for the model to connect them.
And that is the fundamental constraint the authors of this paper wanted to break. They wanted to smash that sequential bottleneck.
They wanted to connect information without any regard to distance.
So enter the transformer.
Enter the transformer.
This is the hero of our story. The paper proposes this totally new architecture that eschews recurrence entirely. So how does it actually solve that telephone game problem?
By relying entirely on an attention mechanism to draw global dependencies. The headline feature here is parallelization.
Okay.
Because the transformer doesn't process sequentially. It doesn't wait for word 1 to finish before looking at word 2. It can process the whole sentence at once.
It just drinks the whole milkshake in one gulp.
Ideally, yes.
Yeah.
It dumps the entire sequence onto the GPU simultaneously. And this changes the math completely. Remember how I said the old models struggled with distance?
Yeah, the operations grew linearly or logarithmically.
Right. In the transformer, the number of operations to relate any two positions in a sequence is constant. It's O of 1.
Wait, let me make sure I'm getting this. So it doesn't matter if 2 words are 5 words apart or 500 words apart.
It does not matter. The model sees the connection between them equally well. It reduces the path length for the signal to traverse from the length of the sentence down to just one step.
That is a massive shift. It's like turning on the lights in a dark room and seeing everything at once versus walking around with a tiny flashlight.
That's a really great analogy. That's exactly what it's doing.
So let's look under the hood a bit. What does this thing actually look like? The paper describes an encoder-decoder structure.
Right, which was still a classic structure for things like translation at the time. You have an encoder that takes the input, say an English sentence, and creates a mathematical representation of it.
And then the decoder takes that representation and generates the output like the German translation.
Exactly. But the ingredients inside are very different from the old models. The encoder is a stack of identical layers. In the paper, they used n equals 6 layers.
It's layered.
And the decoder is also a stack of n equals 6 identical layers.
And what's actually flowing through these stacks?
Data moves through what they call self-attention mechanisms and also point-wise feed-forward networks. They also use residual connections, which help prevent information loss and layer normalization at every step to keep the training stable.
Okay, you dropped the magic word again? Attention. This is the namesake of the paper, so we really need to deep dive into these mechanics, because this is where the actual magic happens. The paper defines something called scaled dot product attention.
Yes. This is the core engine. Honestly, if you understand this, you understand modern AI.
Let's unpack it then. The paper talks about 3 specific vectors: queries, keys, and values. Q, K, and V. This sounds a lot like a database concept.
It's very similar to a retrieval system, actually. That's the best way to think about it. Think of a search engine or even just a physical filing cabinet system.
Okay, I'm picturing a library.
The query is what you are looking for. It's the topic you want to find information on. Let's say you are a word in a sentence and you want to know, who is my subject? Your query vector represents that desire for information.
Got it. So I'm the word sat, and I'm sending out a search query for a noun.
Exactly. Now, every other word in the sentence has a key. The key is like the label on the book spine or the tab on the folder. You compare your query against all these keys to see what matches.
So the word sat checks the key for cat, checks the key for Matt, checks the key for...
Right, and the value. The value is the actual content inside the folder. So the attention mechanism calculates the compatibility between your query and the keys.
Okay.
If there's a strong match like sat and cat, you pull out more of that value.
So if sat matches strongly with cat, it essentially absorbs a lot of catness.
Exactly. It updates its own representation with information from the word cat, and the math behind this is surprisingly elegant. They use a dot product to determine that compatibility.
Now, for the non-math majors listening, a dot product is basically checking if two arrows point in the same direction, right?
Yes, essentially. If the vectors point in the exact same direction, the dot product is high, meaning high relevance. If they're perpendicular, it's 0.
Makes sense.
So they take these dot products, apply a softmax function.
Which basically turns them into probabilities, right?
Right. It turns them into weights that sum up to 1. So you might attend 90% to the word cat and 10% to the word mat and 0% to the word the. And then you just calculate a weighted sum of the values.
Now, there's a word in the title of this mechanism that we skipped. Scaled. Scaled dot product attention. Why do they need to scale it?
This is a really crucial technical detail. They divide the dot products by the square root of the dimension of the keys.
The square root of the dimension. That seems very specific. Why?
Because as models get smarter, those dimensions get larger. And when the dimensions are large, the dot products can get huge.
Okay.
When you feed huge numbers into a softmax function, the function gets pushed into regions where the gradients are extremely small, almost 0.
Ah, the dreaded vanishing gradient problem.
Exactly. Imagine the softmax curve. At the far extremes, it's totally flat. If the gradient is 0, the model can't learn. It literally doesn't know which way to adjust its weights to get better.
So it's just stuck.
Yes. The scaling factor keeps the numbers in the Goldilocks zone. That sweet spot where the gradients are nice and steep, so the model can actually learn efficiently.
That is a fascinating bit of engineering. It's like putting a governor on an engine so it doesn't just blow itself apart.
That's exactly what it is.
Okay, so we have this attention mechanism that lets words look at other words to find context. But the authors didn't just use one attention mechanism. They used something called multi-head attention.
Right. They found that a single attention head was actually pretty limiting. If you only have one head, you're basically averaging all the attention weights together.
Okay.
It's like trying to listen to a symphony, but you've smashed all the instruments into a single mono audio track. You just lose all the nuance.
You hear the song, but you can't pick out the cello.
Exactly. So they innovated. In the paper, they used H equals 8 parallel attention layers, or heads.
8 heads.
Think of it like looking at an object through 8 different color filters simultaneously.
Okay, I like that. 8 different perspectives on the same sentence.
Right. One head might be focusing entirely on grammar, like is this a noun or a verb? Another head might be focusing on semantic relationships, who is doing the action. Another might look at punctuation or tone.
So they project these queries, keys, and values into different subspaces.
Exactly. They run the attention function in parallel 8 times. Then they concatenate the outputs and project them back together.
Wow.
This allows the model to attend to information from different representation subspaces at different positions simultaneously. It gives a complete, rich 3D picture of the language.
It's amazing to think about. Instead of one blurry average view, you get 8 sharp, distinct perspectives combined into one. It creates a much more robust understanding.
It really does. But there's a missing piece here. We talked about how the transformer processes everything in parallel, right?
Yeah.
It sees the bag of words all at once.
The bag of words problem.
Yes. If I give you the words man, bites, and dog, the order absolutely determines whether it's a standard news story or a tragedy.
Right. Man bites dog is very different from dog bites man.
Exactly. And if the model eats the whole sentence at once, how does it know which word came first? To the model, it's just a soup of vectors.
Without recurrence, there is no inherent sense of time or order.
Right. So the authors had to invent a way to inject that order back in. They call it positional encodings.
How does that work? Are they just numbering the words 1, 2, 3?
It's a bit more sophisticated than just integers. If you just use plain integers, the values get way too big for really long sentences, so they add a vector to each input embedding that represents its position. But the way they calculate this vector is what's fascinating.
Okay.
They used sine and cosine functions of different frequencies.
Trigonometry. We're back in high school math class.
We really are. For each dimension of the position encoding, they use a sinusoid. And the wavelengths form a geometric progression from 2 pi all the way to 10,000 times 2 pi.
Why sines and cosines, though? That seems, I don't know, very analog for a digital problem.
They hypothesized that this would allow the model to easily learn to attend by relative positions. Think about a clock face. You have a second hand, a minute hand, an hour hand. By looking at the combination of those hands, you know exactly where you are in time.
Okay, I can visualize that.
The sinusoids work similarly. They create a unique continuous pattern for every position. But the real beauty is the math. For any fixed offset k, the positional encoding at position pos plus k can be represented as a linear function of the encoding at position pos.
Oh, I see. So the model can literally do math on the positions. It gives the model a sense of spatial awareness within the sentence. It inherently knows that dog is exactly 3 steps away from man.
Exactly. And another benefit they mention is that it might allow the model to extrapolate sequence lengths way longer than the ones it saw during training, because it's a continuous function, not just a hard-coded index.
That's brilliant. So we have the transformer. It's parallel. It uses multi-head attention to see different contexts. It uses positional encodings to understand order. Now we have to get to the bottom line, the results. Did it actually work?
It didn't just work. It set a completely new standard. It absolutely obliterated the benchmarks.
Let's talk numbers. Because usually when you introduce a fancy new architecture, there's a trade-off, right? It's smarter, but it's way slower, or it needs a ridiculous amount of data.
Not this time. They tested this on machine translation, specifically the WMT 2014 English to German task, and they achieved a BLEU score of 28.4.
And for context for our listeners, BLEU is a metric for translation quality. Is 28.4 good?
In the world of NLP research in 2017, it was massive. That score beat the previous best results, which, by the way, included huge ensembles of multiple models stitched together by over 2.0 points.
A full 2-point jump is significant.
It's a generational leap, and on the English to French task, even more impressive. They achieved 41.0 BLEU, establishing a new single model state-of-the-art.
But here's the part that I think really caused the explosion we see today. It wasn't just the quality, it was the speed.
This is the truly shocking part. The paper details their training costs. Their big model, the one that broke all the records, was trained on 8 NVIDIA P100 GPUs.
Just 8?
Just 8. And it took 3.5 days.
3.5 days on 8 carts.
Compare that to the competition at the time. Other models like ByteNet or GNMT were taking huge resources or significantly longer times just to reach lower performance. Some competitors used hundreds of GPUs for weeks.
Wow.
And their base transformer model, it reached a really high level of performance after training for just 12 hours.
12 hours. That completely democratizes the research. Suddenly, you don't need a massive Google-sized supercomputer to build a state-of-the-art model. A university lab could do it. A tiny startup could do it.
Exactly. And the complexity analysis in the paper shows exactly why. Self-attention layers are just inherently faster than recurrent layers when the sequence length n is smaller than the representation dimension d.
And since that is typical for most language tasks, the transformer is just built to be more efficient.
It is. It's lighter, faster, smarter. And interestingly, they found it was more interpretable.
How so? Because usually deep learning is just a black box. We put data in, magic math happens, an answer comes out.
Right, but the authors noted that with self-attention, you can actually visualize where the model is looking. Because the attention weights are just numbers between 0 and 1, you can just plot them on a graph.
Oh, right, you can see the heat map. You can literally see, oh, the model is strongly connecting the pronoun it to the word animal.
Exactly. In the appendix of the paper, they actually show these visualizations. They saw that individual attention heads were clearly learning to perform entirely different tasks. One head was handling long-distance dependencies, another was handling syntax.
So it wasn't just a black box anymore. You could see the structure of the language emerging organically in the attention maps.
It's almost like watching the brain scan of the AI as it thinks. It learned grammar without ever being taught grammar rules. It just figured out that, hey, if I look at the noun when I'm processing the verb, I get the answer right.
That is so cool. Now, looking at the conclusion of the paper, the authors clearly seem to know they're onto something big. But they're also looking beyond just text.
Yes, they specifically mention their excitement about applying this to input and output modalities other than text. They explicitly call out images, audio, and video.
And sitting here in 2026, looking at the incredibly realistic image and video generators we have everywhere, that was remarkably prescient.
It was the literal blueprint. The transformer architecture didn't just stay confined to text. It became the foundation for almost everything we call generative AI today. Vision transformers, or VITs, which analyze images. That's literally just this paper applied to pixels instead of words. Audio transformers, same exact thing. It all stems from the singular switch to attention.
It turns out attention isn't a language concept at all. It's a universal data processing concept.
That's exactly right.
So to wrap this deep dive up, let's recap the 3 main ingredients that made this 2017 paper the big bang of modern AI.
Sure. First, parallelization. Breaking the sequential chain of RNNs allowed us to use the full power of our hardware. It let us scale up massively. Second, multi-head attention, allowing the model to look at the data from multiple perspectives simultaneously to capture all that nuance and depth.
And third, Positional encoding. Injecting order back into the chaos so the model understands the structure of the sequence without being constrained by sequential time steps.
That is the trifecta.
It's so fascinating. The shift from sequential to parallel didn't just make things faster. It allowed models to scale to sizes that were previously thought absolutely impossible. We went from training on millions of words to trillions of words.
And that massive scale is what unlocked the emergent abilities we see today. But, there's one provocative thought I want to leave you with before we go.
What's that?
We spent the last 15 minutes or so talking about how the transformer killed the sequential bottleneck, how it drinks the whole milkshake in one gulp.
Yes.
But did it? Completely.
You're talking about the generation phase.
I am. The paper explains that the training is parallel. The encoder looks at everything at once. But the decoder, the part that actually writes the response,
It's still autoregressive, meaning
it still produces one token at a time. It predicts word 1, feeds it back in, predicts word 2, feeds it back in.
So when you ask ChatGPT to write you an essay right now in 2026, it's still doing it sequentially, just one word at a time.
Yes. We solved the understanding bottleneck. We can read the whole prompt at once, but we are still generating linearly. The output part is still fundamentally sequential.
So the revolution isn't quite finished yet.
Not entirely. There is still a holy grail out there for researchers, non-autoregressive generation. Can we generate the whole paragraph at once the exact same way the model reads it at once?
So the big question for you to mull over is, have we fully solved the sequential bottleneck yet? Or is that the next big leap waiting for us?
That is the trillion-dollar question. Maybe the next detention is all you need papers being written right now to solve exactly that.
It very well might be. Well, on that note, we want to thank you for listening to this deep dive. We hope this helps you look at the AI tools you use every single day with a little more appreciation for the architecture humming underneath.
Be attentive to the patterns in your own learning, everyone.
See you next time.